Hello again, everyone. Welcome to our discussion of section 4.2, where we will continue about our discussion of polynomials. Last time, we talked about the polynomial function or expression itself, what it looks like, and we talked about multiplicity, we talked about the zeros of the function and factors and all of that. And this time, we're actually going to take the time to graph polynomials manually. We will make use of the stuff we learned in the previous lesson. Before that, I'd like to remind you to please take 30 minutes to 45 minutes to skim through this section of the textbook, 4.2. And as you do that, before you watch this video, take notes of any important things that you might read or anything that you might have questions on. Then watch this video and attend the class and do the same thing. Once again, make note of any questions you might have or any important things you might see or hear that you think that will be important in this topic for you individually. And of course, review this material, the lecture notes that you've taken, and go back to the textbook section, go over all those problems that the book has solved on your own without looking at the solutions. So in this case, it would be graphing polynomials. So write down the polynomial that you see graphed in the textbook, but without looking at the graph. Then graph it on your own and then compare your solution with that. Do the same thing with the examples that I give in the video without looking at the solutions. And then, of course, please complete all the homework for this assignment, for this section, by the due date. And then please don't forget to review previous sections, previous lessons, and all you need to spend time, the only time you need to spend on that, I think half an hour a week should be enough. But you do want to spend some time reviewing the previous material. All right. So here, before we start graphing the polynomial, we need to remember some of the things. Determine the zeros of the polynomial. Factoring the polynomial may become necessary. It's actually not may become, it is necessary. So the factoring of the polynomial is necessary. And determine the multiplicity of the polynomial. We've talked about this at length last time. This is the power of each factor, right, is the multiplicity. The other thing that we have not yet talked about is the number of turning points. Last time we did discuss the degree of a polynomial, right? The degree of the polynomial is the highest power of any of x in that polynomial. That's the degree of a polynomial. Looking at that number, that highest power, subtracted by 1, so n minus 1 would be the number of turning points in a graph of the polynomial. So if the highest power is 4, then the maximum, not that we will have 3 turning points in the graph, but at most, the graph has at most these many turning points. And turning points are where the relative minimum and the graph will change from where there are relative minimum and maximums. Those are the turning points. Okay. We've talked about relative minimum and maximum way early in the course. Remember, it was maybe the first lesson or the second lesson of this course was about identifying the relative minimum and maximum. I could be wrong on that, but it was one of the earliest ones. I'm not sure it was the first or second lesson. But how many of those turning points or relative minimum and maximums can we have? We can have a maximum of n minus 1. So if a polynomial has a highest power of 9, then the maximum number of turning points we might have is 8. Oftentimes we might not have 8, but we might have 4 or 3. but the maximum of turning points we can have would be 8. Okay, so determine the x-intercepts, and these are the zeros of the polynomial, right? And the graph has at most, once again, n x-intercepts or n zeros. Again, that n refers to the degree of the polynomial. Let me make that clear because I don't think my worksheet is clear on that. So n is the degree of the polynomial. Okay, that's that. And then determine the y-intercepts, the x-intercepts, and graph the polynomial. So we need to know the multiplicity of the zeros. We need to know the zeros, which are the x-intercepts. We need to know the y-intercepts, and we need to know the multiplicity and that. And of course, before that, we want to make sure that the polynomial is in factored form. That's very, very important. Factor the polynomial. Okay, first step. Okay, the intermediate value theorem. Remember that? In the last video for section 4.1, usually when I talk about this in class, because there is not enough time to talk about everything, I probably would skip this during the class lecture, but fortunately for video, both you and I can relax and cover everything that is important. So this is one of the things I talked about in the last video, the intermediate value theorem, which is where if you have, we talked about this on the computer, but let me draw a little graph here, just as a reminder, but we did talk about this last class, which is good. So you have a background about this. So suppose we have a polynomial that graphs like this, right? Suppose the graph of the polynomial looks like that, right? So clearly we have zeros here, here, and here, and here, right? The intermediate value theorem is a way to predict whether you have a zero between two numbers or not. Okay? Suppose we pick some number here. Suppose I pick A and I pick B. Right? A and B are two numbers along the x-axis, just like what you see in this box. If you evaluate the polynomial, or p of x, at A, and evaluate the polynomial at B, and we find that p of A and p of B have opposite signs, opposite algebraic signs, then the polynomial has at least one real zero over the interval AB. That means if that AB defines some interval A comma B from A to B, then if the polynomial changes function value when you evaluate it at A and when you evaluate it at B, it goes from positive to negative, right? We can tell from the graph. The value of the function at A is positive because the graph is above the x-axis. And if you evaluate p of x at B, it's going to be some negative number because the graph is below the x-axis. So if this is saying if they have opposite signs, p of A in this case, in this example, so this box is talking about generally, but in this example, p of A would be positive, and P of B would be negative. Do you see why, right? P of A would be positive, P of B would be negative. So we have a switch in algebraic sign. We go from positive to negative. right? Because we're reading the graph from left to right. So this switch in algebraic sign for the value of the function indicates that we must have a 0 between a and b. Somewhere between a and b there must be, sorry, not that and that, but between a and b there must be a 0 of the function. That's what that intermediate value theorem is saying. It's predicting that without us actually finding this. Okay, imagine that the graph didn't exist, right? Could you predict if there is a 0 between a and b? Yes, you would simply plug in that value inside the polynomial and note the sign, algebraic sign for it. Then you would plug in b in the polynomial and note the algebraic sign for it. Because there's a change in algebraic sign, that means the line must have gone through the x-axis at some point, because that's how the shift in algebraic sign happens. Okay, and that's intermediate value theorem. Okay, having said that, for each polynomial below, determine the maximum number of real zeros, i.e. the maximum number of x-intercepts. Well, let's put these terms in order, right? They're not in order because the highest power should happen first. So f of x equals minus x to the 6th power plus x to the 4th power minus x squared plus 3. Now, determine the maximum number of real zeros. The maximum number of real zeros is going to be 6. It's not going to be beyond the power, the highest power in the polynomial. So the maximum number of zeros, the real zeros, is equal to 6. Suppose you find 4 real zeros, then what? What about the other 2? The other 2 would be complex numbers. Okay? So that's what that means. But the maximum, if all the zeros of the polynomial are real value, real number values, then it cannot exceed 6. The number equal to the highest power in the polynomial. Okay? What else they ask us to answer? So that's the x-intercepts are the same thing as real zeros, and the maximum number of turning points. Remember, the turning points has a formula, right? That's the formula for determining the turning points. n minus 1, and n is the degree of the polynomial. So for this example, n minus 1 would be 6 minus 1, 5 would be the maximum number of turning points. Okay? So that's all they're asking us to do for that. For the second part, please pause the video, answer the same question for this polynomial, and then look at my answer to compare with your own solution. So here the terms are in proper order. The maximum number of real zeros must be 4, the maximum, right? And the maximum number of turning points like that. Okay, so here we have to go through all those steps that we mentioned earlier, which is find the factor this expression, find the zeros of it or the x-intercepts of it, find the y-intercept, and then noting the multiplicity of all those zeros, because we need to know, remember, we're not doing this with technology, so we need to know where the line should cross the x-axis and where it should not, right? So we need the factors of this polynomial. Okay, to factor this, which one of the factoring methods could you use here? We discussed some of the factoring methods earlier, right? So mixed factoring should be applied here. Mixed factoring meaning just take out any common factors. So x squared would be a common factor among all three terms. So g of x would be equal to x squared times x squared, right? X squared times x squared gives us x to the fourth. So what should I put next to multiply by x squared and get minus 4x cubed? Minus 4x, right? Minus 4x times x squared is minus 4x cubed. Plus, what should I put here to multiply by x squared and get 3x squared? 3, right? Remember, factoring is the opposite of the distributive property. So if you distribute this back into this factor, into this parentheses, you should get the original expression back. If you don't, then you have to adjust your factoring, right? X squared times x squared, x to the fourth, minus minus. 4x times x squared is x cubed because the powers add to each other. We talked about this. I would imagine we would talk about this in a very early course like Math 96 or something, where if you multiply variables or terms that have the same base but different powers, the powers add to each other. Okay, so that's that. That's 2 plus 1 is 3. So 3 times x squared is 3x squared. So we're okay with the factoring here, but can we stop here, or can we factor this a little more? We can factor this a little more, right? This is an easy quadratic function to factor. So let's factor it. We would end up with x minus 3 times x minus 1. So that's the full factorization of that original expression. Okay, so now we have the factors. Where are the zeros or the x-intercepts? So x-intercepts, let's find those. And multiplicity, and their multiplicity, right? X-intercepts. So, for one thing, x squared equals 0, then x equals 0. Right? That's one of the x-intercepts. I meant to say 0, 0. Sorry. That's that. That's the x-intercept. And also the other factor, set that one equal to 0. This is why we factor, right? So we can do this. We can find the zeros very quickly. X minus 3 equals 0, then x equals 3. Right? So the x-intercept at that location is 3, 0. That's another x-intercept. And that factor, x minus 1, set that one equal to 0. Therefore, x equals 1. So the x-intercept would be 1, 0. Like that. So those are the x-intercepts. How about the y-intercept? The y-intercept happens when x values are 0. And I'm sure as you look at that, it's y and x-intercepts are at origin, right there. So if you plug in for that, for x with 0, in any of these equations, if you plug in for x with 0, let's say the original one, that would be z to the fourth minus 4, 0 cubed, plus 3 times 0 squared, that would be equal to 0. So 0, 0 is not only the x-intercept, but also the y-intercept. Okay, like that. So we have enough information now to plot this. We factored it. I mean, we can, right? We went through the list. We did all this. We factored it. We determined we're going to determine the multiplicity. That's easy. The multiplicity of this factor x equals 0 is 2. So it means at that point, the graph is going to hit the x-axis and bounce back to the same side, whichever side that is, negative or positive side of the y-axis. And for x minus 3 and x minus 1, the multiplicities are odd, which are 1. Okay? And then we found the x-intercepts, y-intercepts, and graph the polynomial. There's something else that we need to do that we may have to do. I'm not sure if we have to do it in this case or not. It's easy to do, but it's something that we only have to do sometimes. That's why I didn't include it as part of the list. And let's see, let's graph this, and if we get to that point that we have to do this, to use this technique, then I'll explain it. But let's first identify all these points, x and y intercepts, on the graph, right? So 0, 0 is both the x and the y intercept, so it's right there. 3, 0 is the x-intercept, right there. Y, 1, 0, right there. And 0, 0. Okay, so now we know that the line of the graph is going to hit the 0, 0, or the origin, and bounce back to the same side, because that's 0, x squared has even multiplicity. Right? So the line is not going to cross the x-axis at the origin. It's going to bounce back to the same side. But here's the question. Where is the line of the polynomial, or the graph of the polynomial, approaching the origin? Is it coming from above the x-axis, or is it coming from below the x-axis? Is it doing this, or doing that, or doing this? Do you see that, what I mean? We don't know where the line of the graph is approaching. We know at x equals 0, 0, at the origin, at point 0, 0, not x 0, 0, but at point 0, 0, the line of the graph is going to bounce back. But to which side? If the line is coming from below, it's going to bounce back to the same side, like that. But if the line is coming from above, it's going to do that. So we need to find out from which side, above or below the x-axis, is the line of the graph approaching this 0. Okay? And that's what I was saying. Sometimes you might have to do this. So it's easy. All we have to do is pick some random value on the left side. Let's say -2. And x equals -2. Evaluate the function at x equals -2 and see what algebraic sign that value has. The value itself, the function value itself, is not important. What we're looking for is the algebraic sign of the function value at -2, at x equals -2. So let's find that out. Because if it is positive, then the line must be coming from above the x-axis. If the function value at -2 is negative, then the line must be coming from below the x-axis. Okay? Okay, so I'm going to do that here at the bottom. So the g of x at -2 is equal to, that's not part of the x-intercept, so I want to distinguish that. That's why let me draw that line. So g at equal to -2 is -2 to the 4th power minus 2 times -2 cubed plus 3 times -2 squared. Okay, so -2 to the 4th power is positive 16. -2 cubed is -8 times -4, it is positive 32. Negative 2 squared is positive 4 times 3 is positive 12. So we end up with a positive value. I'm not going to add these, and I want to put just plus, because as you read these notes on your own, because I'm going to post these notes on Canvas, so you have the videos as well as these notes to look over. I want to put the positive only because I want to highlight the fact that we don't really care about the value of this function at negative 2. We care about the sign of it, the algebraic sign. It's positive. So the line then, we established, the line is coming from way up high here. It's coming down from here. When it hits 0, 0, that 0 has even multiplicity. So it's going to bounce back to the same side. It's going to come up and it's going to go back and it's going to go through these 2 points, crossing the x-axis. Why? Because those two zeros, these two, have odd multiplicity. Look at that. The power of x minus 3 is 1. The power of x minus 1 is 1, which is odd, right? So this line, it's going to do this. It's going to come here, hit that, and go bounce back, go up like this, come back down again like this, cross the x-axis. At some point, it's going to curve back up again and go right through that. Like that. So that's a rough manual sketch of that polynomial. Okay? In calculus, you're going to have more details about this, how to draw these graphs even more perfectly. For example, here, notice the highest power, 4. So we would expect a maximum of 3 turning points, right? N minus 1, 3 turning points. Maximum. Not that we would have these many turning points, maximum of turning points, 3. So do we have 3 turning points? Yes. 1, 2, 3. Right? So this one is relative minimum, relative maximum, relative minimum again. That's what turning points are. But here, then, that's just a maximum. So we may or may not have that many. When you actually draw the graph, we may have just 2. Okay, so that's what that is saying. So we have a maximum of turning points, and we did find 3 turning points. So guess what? That means this polynomial has no more turning points. That means on this side, it'll keep going up forever. On that side, it'll keep going up forever. And the arms never turn back down again. There are no more turning points. We have found maximum number of turning points. So in other words, if you know that about a function, about a polynomial, then you know that must be the absolute minimum. Because you know these lines will never turn back, and the lowest point of the graph here is that point. So that would be the absolute minimum. Okay? All right. So let's look at this next polynomial. Once again, we need to factor this, right? So let's do that. So f of x, this is an easy quadratic function. Quadratic functions are a polynomial as long as the x is not in radical form or doesn't have an irrational exponent like over here. So we can easily factor this into x minus 4 times x minus 1, right? If you FOIL this, these factors, you're going to get that back. So it was an easy equation to factor. Now, let's find the x-intercepts and the y-intercepts. So the are also zeros of the polynomial, right? So x minus 4 equals 0. Then we have x equals 4. Then for x minus 1 equals 0, we have x equals 1. So those are the x-intercept here is 4 comma 0 and 1 comma 0 here, and the y-intercepts is wherever the x values are 0. So f at 0 is 0 squared minus 5 times 0 plus 4. So that is equal to 4. So we have 0 comma 4 as the, so these are the x-intercepts, and this is the y-intercept, okay? So we might have to test, just like that, what we did for the previous exercise. We might have to test a point to see from which side the line of the graph is approaching each of these zeros. Okay, so 4 comma 0 would be here, 1 comma 0 would be here, and 0 comma 4 would be here, right? All right, so we know that the line of the graph is hitting the x minus 1 comma 0, that one. And we know that it's going to cross the x-axis, right? Because the power of that 0, x minus 1, is 1. So is the power of x minus 4. So both have odd powers, which means the line of the graph must go through right through this one and right through that one. Okay? So if that's the case, then we know, in this case, it's obvious that the line must come from here, right? It's going to come from here, hit this point, dip below the x-axis, and then come back up again like that. Because this is a quadratic equality or function, so we don't have to really, it has a much simpler graph than something like that. Okay, so we can draw it quickly. So like that, like this, and curve back up again, and go like that. So here, according to the rule, n minus 1 would be equal to 2 minus 1 equal to 1. We would expect a maximum of turning points So we would expect to see maximum of 1 turning point. There you have it, 1 turning point. So that is the absolute minimum, okay? Because we know that there will be no more turning points. So these arms will keep increasing forever, okay? That's that. Okay, once again, so here this is nice because the expression is already in factored form, right? So we can go directly to our x-intercepts. Okay. So each factor, set them equal to 0. So 0 comma 0 is one of the x-intercepts. Then x minus 1 equal to 0. You have x equals 1. So you have 1 comma 0 as the other x-intercept. X plus 3 equals 0. So x equals negative 3, which means negative 3 comma 0 is another x-intercept, and finally x plus 5 equals 0, and we have x equals negative 5 or negative 5 comma 0 as the x-intercept. And how about the y-intercept? So for that, plug in for x with 0 and calculate the value of the function. So the function at 0 would be, it would be 0, right? We know that. 0 times 0 minus 1 times 0 plus 3 times 0 plus 5, that would be 0. So we would have 0 comma 0 as both the x and the y-intercept. The y-intercept and the x-intercept. Okay, so these are nice, easy numbers. So I'm going to increment the axes here with the same easy numbers. So negative 1, negative 2, negative 3, negative 4, and negative 5, right? So negative 3 comma 0, that's 1, 0. Negative 5 comma 0, that's another one. 1 comma 0, that would be that. 0 comma 0, that would be that, and which is also the y-intercept. So we know, look at the power of all these factors. The power is 1 for all of them, right? So the multiplicity of all these zeros is odd, which means at all these points, the line is going to cross the x-axis. It's going to cross the x-axis at all these points. So I'm going to begin from here. You can begin from here or here. It makes no difference. But if I'm starting from this side, I want to know from which side should I approach this point. Should I approach it from below the x-axis? Or should I approach this point from above the x-axis? At this point, I have no idea. So in that case, let's pick a random number to the left of this and evaluate the function at that. Because whatever the algebraic sign of the function at that point tells us if it's negative, then the line is coming from below. If it's positive, it means the line is coming from above. Okay, so let's pick some test point for that. So I'm going to write that up here. Let me actually add that to know to find from above or, oops, my ink is drying here. To find from above or below the x-axis, the graph is approaching, let's say, minus 5 comma 0. To find that out, what do? Let's pick a number, x value like negative 6. So function at negative 6 equals negative 6 times, I'm plugging in negative 6 here, times negative 6 minus 1 times negative 6 plus 3 times negative 6 plus 5. Notice we do not care about the value of the function at negative 6. What we care about the algebraic sign of the value of the function at that point. So I'm going to do this. Instead of value, I'm going to replace each factor with the algebraic sign. So minus 6 is minus times minus 6 minus 1, it's going to give us another negative value. Minus 6 plus 3, it's going to give us another negative value. Minus 6 plus 5, it's going to give us another negative value, right? So for each factor, we're going to end up with a negative value. 4 negative values multiplied by each other, what do we get? We get a positive final value because we have, if you multiply even number of negative numbers, you get a positive number. If you multiply an odd number of negative numbers, like 3 of them, you get a negative result. So we know with this quick test, we established that that if we are on the left side of this, if I picked -6 and I ended up with a positive function value, so the line must be coming from above the x-axis, because the function value at an x that I picked randomly from this side turned out to be positive. So the function value is positive. So and remember, all of these have odd multiplicity, so I must pass through the x-axis and come up again in all of them. But now I know from which side I should approach this point, not from below, from above. Why? Because now I established that with this test. Okay, so the line is coming like this, going through that, coming back up again, doing like this, turning back down, going through that point, and then turning back up again and going like that, like that, like that. Okay, that's roughly a manual sketch of that polynomial. In calculus, we will look at exactly where these turning points happen. In other words, here I estimated it. That is not a topic we look at in this course. But in calculus, we know exactly where this turn happens. At which x value and y value that turn happens. We know exactly where that is. Okay? And if you look at the polynomial, x times x times x times x gives us an x to power 4, right? So we know we could expect a maximum of 3 turning points. Do we have three turning points? 1, 2, 3. So the graph is okay in that respect too. It has adequate number of turning points, or turning points that make sense at least. All right, so let's look at the next one. This one is also a factored form, so that's great. It cuts down on the amount of work for us, so it's easier to deal with these kinds of polynomials. Let's find the x-intercepts. So x equals 0, that means 0, 0 is the x-intercept. Set x minus 3 equals to 0, then x equals 3. So we have 3, 0 as a 0. Oh, x minus 3 and x minus 3. So that, let me rewrite this then. We need to combine these. I just noticed it again. So this is equal to minus x times x minus 3 squared times x plus 2. So 3 has multiplicity even. That means at this 0, the line of the graph does not cross the x-axis, or is not going to cross the x-axis, but it bounces back to the same side where the line is approaching. And then finally, x plus 2 equals 0. And this is x equals negative 2. So we have negative 2, 0 as the next 0 of this polynomial. Okay, the y-intercepts, or y-intercept, we should have one of those. Okay, so that's also the 0, 0, right? You can see it easily. If you put 0 for x, I'll do it anyway. So this is just 0. And 0 minus 3 squared, and 0 plus 2. So this 0 in front will make all of this 0. So we have 0, 0 also functioning as the, or acting as the y-intercept. So 0, 0 is y-intercept as well as x-intercept. Okay, let's plot these points. And these are easy numbers to plot. So 1, 2, 1, 2, 3, and -1, -2. Okay, 0, 0 would be that point. 3, 0 would be that point. -2, 0 would be that point, and that. Okay, so now, once again, we know that at this point, at 3, 0, the line of the graph, because multiplicity is even, the line of the graph is going to bounce back to the same side. If the line is approaching from this side, it's going to go that side. If the line is approaching from below, like that, it's going to bounce back to the same side. But the question now for us is, I'm going to draw this graph from left to right. When I do that, I want to know whether my line, whether I should draw my line from here, like that. I know at -2, 0, the line should go across the x-axis. So if I'm coming from below, the line should go right through. If I'm coming from above, the line should cross the x-axis like that. But I need to test the function value at some random number to the left side. Let's say -3. Is it negative? Is the value of the function on this side negative or positive? If it's negative, then the line must be coming from below. If the function value on this side is positive, then the graph line must be coming from above. So let me pick some number, easy number, say -4, right? -4 would be somewhere here. So I'm going to test that. So let me write this down because you should have it in your notes. To see from which side the graph line is approaching -2, 0, right? Approaching -2, 0. Let's pick, just like I said, let's pick -4, right? So h at -4. Let me see if I can bring this up. You can barely see everything on the screen. As much as possible, I like to put everything on the screen. So there, you have the function up there. So this function at -4, we have, again, we don't care about the value of the function at -4. We care about the algebraic sign of the function at -4. So -4, I'm just plugging in -4 here, times -4 minus 3 times that's squared, and then -4 plus 2. Okay, so I'm just going to write down the algebraic signs. We have this minus in front, right? Take a look at that. We have a minus in front. So minus times x, that's -4, so that's another minus value. Minus, this is going to be positive, right? -7 squared, it's going to be some positive value. -4 plus 2, it's going to give us some negative value. So minus times minus times plus times minus, we have a minus result. The result is negative. So that means the line of the graph must come from below, because I picked x equals -4 to evaluate the function at, and it was negative. So the line is coming from below, right? So this is what the line is doing. And it is, I want to just remember which one. So x minus 3. At this point, the line of the graph, it's going to bounce back to the same side, right? Because it's got even multiplicity. All right, so the line has to do this, then come back down towards the x and y intercepts. It's going to go right through the x-axis. When it hits this, 3 comma 0, be careful because 3 comma 0 has multiplicity even. So it cannot, the line cannot go through, it's going to bounce back to the same side like that. So this is a manual construction of the graph of that polynomial. So if you multiply all these x times x times x times x is x to the 4, right? How many turning points will that give us? N minus 1. So 4 minus 1, 3. We would expect a maximum of 3 turning points. Do we have 3 turning points? 1, 2, 3. So we do have a maximum of 3 turning points. So knowing that, what use does it have? So, well, for a person, say, living, or a mathematician, not a person, but a mathematician living 200, 300, 400 years ago, where they don't have access to technology, they could quickly identify this point as the absolute maximum. Because if you know there are no more turning points than the 3 that you already identified, then these lines will keep dropping on both sides towards negative infinity. So that point becomes absolute maximum. And these become relative minimum and then relative maximum. Relative maximum, relative minimum, absolute maximum. Okay? Okay. So that's that. In this case, this one again not factored. So we have our work cut out for us here. But no problem, right? Because we have all the tools we need to graph this. Let's see. So we need to factor this, right? So let's start with what we know. At this point, the only common factor is x. So h of x, let me move this a little bit over like this. So h of x is equal to x, factor out x. What should I put here? What term should I put here to multiply by x to give me x to the 5th power? Well, we know that if the bases are the same, the powers get added. These are the properties of the exponents. If you've forgotten them, please Google it or go back to the textbook section where this is and make sure that you refresh your mind on that. So we're using that knowledge from the previous sections or previous material. The bases are the same, so we can add the powers. That means this power should be 4. Now, x times x to the 4, it's x to the 5th. For this one, minus minus. What should I put here so that if I multiply by x, I get minus 5x cubed? So minus is already there. I certainly need a 5. What else do I need? X to what power? The summation of these two powers should add up to 3. So 1 plus 2, right? And finally, all I need to multiply by x to get 4x is plus 4, right? So far, we can do that. So x is a factor of that polynomial. Well, what about this expression? Do you remember of any technique we've learned before that can help us factor this polynomial on the inside of the parentheses? Do you remember a technique? Should I remind you? Do you remember the very useful U substitution method? Let's use it. So for this piece, let U be that term, x squared. Okay? Then we can rewrite this. We want to factor this term. We're okay with this. This is happy. It's already been factored out. We want to factor these 3 terms. So we can use the U substitution method to rewrite this as a quadratic equation. So that'll be x squared. If U is x squared, I meant, let me use my thicker pen here. This is U squared, then let u become x squared. Then rewriting that, we have u squared minus 5u plus 4. Okay? So that's what happened. We used this substitution, and now we have that. That is written as that. Is that easy to factor or what? This is an easy quadratic function to factor, right? We write u minus 4 times u minus 1, right? That's the factorization of that. Now let's solve for each factor. So u minus 4 equals 0, then u equals 4. U minus 1 equals 0, then u equals 1. Are we done? No. We found u, not x. We need to find x. So if u equals 4, then we have 4 equals x squared. So x equals plus or minus 2. Okay, so then let's see. So this is 4. Is that true? Yes. So taking the square root of both sides, we end up with x equals plus or minus 2. Okay. Then if u equals 1, then 1, we're substituting back into this to calculate x. 1 equals x squared, then x equals plus or minus 1. Okay, so now we could write down the full factorization of that expression. So we have the so this is from here. Maybe I can barely fit everything on the screen there. So we have h of x equals x, which is that first factor, times x values minus 2 and plus 2. So we have x minus 2 times x plus 2, and then times x plus 1 times x minus 1. Okay. So we found all the zeros in u terms, then all the zeros in x terms. That's what we're looking for. The u substitution method is just a technique to help us solve for the zeros. We figured out all the u's, and then using u's, we figured out the zeros of the polynomial, and we use that to write the factors. So this is all the factors of the original polynomial, and we cannot combine these because these are different, right? So all of these have multiplicity or power 1, because the power of each of these factors is 1, which is odd. So at all of these zeros, and I should write those here. I should write them down so that it's clear. Yeah, I need to identify those. I didn't do that. But now we can easily write down each of the zeros, right? I'm running out of space here. So let me try to squeeze the rest of this here. So at x equals 0, we have 0, comma 0. That's one of the zeros of the polynomial. X at 2, comma 0, right? Set this equal to 0, solve for x. What do you get? You get 2, comma 0. Set this x plus 2 equals 0, you get minus 2, comma 0, another 0 of the polynomial. From this factor, x plus 1, set it equal to 0, solve for x. What do you get? You get negative 1, comma 0. Set this factor, x minus 1, to 0, and solve for x. You get 1 comma 0, right? And the y-intercept, if you look at this original function, the y-intercept is the same thing as the x-intercept here. 0 comma 0 is both in this case. Okay, so let's plot these points on the graph. So did you notice that that's why I asked you guys to review previous material, because today in this lesson, we use grouping? I think it was the previous one, not in this lesson, but maybe 4.1. We used factoring by grouping in one of these lessons. I think it was 4.1. And here we're using the method, U substitution method. So please be aware that all of the previous skills that we've learned can come up anytime. And we need to be ready to access them. And the only way to do that is to refresh our mind regularly each week. Okay? So it only takes half an hour a week to refresh your mind about the previous material. Okay, so now let's plot these points. These are, again, easy numbers to plot. So 0 comma 0 would be the origin. 2 comma 0, let me increment these. So 1, 2, negative 1, negative 2, like that. So 2 comma 0 would be that. Negative 2 comma 0 would be that. Negative 1 comma 0, that. 1 comma 0, that. So all of these have multiplicity odds, so I know the graph line goes right through each one, right? It crosses the x-axis at all those points, at all those zeros, or x-intercepts. But from which line? I'd like to begin graphing this polynomial from left to right. So I need to know if the line is coming from above the x-axis, approaching this negative 2 comma 0, or is it coming from below the x-axis? So let's pick a number on the left side, anything on the left side of negative 2. Let's say negative 3, right? Let's evaluate the function at negative 3 and see what is the algebraic sign of the function at that point. I'm going to do that up here. So let me put that here. To determine from which side the graph line is approaching negative 2 comma 0, right? Approaching, let me move this over a little bit, approaching negative 2 comma 0. So this is what we will do. Evaluate this function at negative 3. H at negative 3 equals negative 3 to the 5th power minus, you could put negative 3 here, well, it's off the screen. You can put negative 3 in here or here. It makes no difference. Okay? It would probably be better if you plugged it in here, but I chose that, so it makes no difference. The numbers here are a little bit more difficult than the other expression. So minus 5 times negative 3 cubed plus 4 times negative 3. Okay, once again, we don't care about the values, just the algebraic sign. Negative number raised to an odd power, that's going to be negative. Minus 5 is minus 5 times minus a negative number raised to an odd power power, we get negative, and then minus 3 times 4, negative value, right? Plus a negative value here. So let's see. So here because not everything is being multiplied. It matters what these values are. So it's okay. So minus 3 to the 5th, I can use my calculator here to get a quick feel for what these numbers are. Because in factored form, we wouldn't care about the values, but in here, the function is not in factored form, so we do care about what those values are, because we're going to add or subtract them. So I think here you can see both the calculator screen. So negative 3 to the 5th power minus 243 minus 3 cubed. Oops, the screen went out of focus. Okay, still trying to focus back. Okay, that should be good. So negative 3 squared or cubed is negative 27. Negative 27 times negative 5, so plus negative 27 times negative 5. What do we get? We get negative 108 minus 12. So we get a negative number, right? So negative 120, negative 120. So that is, so I want to, this we can ignore. But that result, this whole thing is equal to negative 120. So what we care about this is that it's a negative number. That means I picked a number, negative 3 on this side of negative 2 comma 0, and it ended up that the function value is negative. So the line must come from below. Okay? So this is what this graph would look like. So this line would come from below. It would cross that, turn back down, go through that, turn back up again, go through the origin, come back down, go through that, and then come back up again and do that. So the highest power of the function here is 5. 5 minus 1, 4. We would expect a maximum of 4 turning points. Do we have 4 turning points? 1, 2, 3, 4, and that's it. So that also tells us that on either side, the graph line, it's going to continue, on this side, it's going to continue rising, and on this side, it's going to continue diving this way. So it will on neither side, the line is going to curve back towards the x-axis again, because we do have the maximum number of turning points. Okay? So that's a rough sketch of this polynomial. Again, the nice thing about this is that we had to remember a method or technique that we have learned before. So I like that about this example. It helps us refresh our mind and remember some of the skills we've learned before. Okay. All right. So next, the example is using the intermediate value theorem. Remember that? We talked about that. If possible, whether the function f has at least one real zero between a and b. So the intermediate value theorem says that evaluate the function at these two endpoints. So this a and b are two points. Evaluate the function at those 2 points and see if the function changes algebraic sign. If it does, then we must have a real zero in between these two, because that's where the transition from one algebraic sign to the next happens. Okay? So let's evaluate the function at these. When they say using the intermediate value theorem, that's what we're doing now. So the function at 1 right? So we have 1 plus 3 minus 9 minus 13. So we have minus 22 minus 20 minus 19, and then minus 19 plus 1 is minus 18, right? So note the algebraic sign at A. It was negative. Let's see if this function, what algebraic sign we will have at the function at 2. So the function at 2, we will have 2 cubed plus 3 times 2 squared minus 9 times 2 minus 13. So 2 cubed is 8. 2 squared is 4. 4 times 3 is 12. Minus 9 times 2 is minus 18. Minus 13. Right? So minus 18 plus minus 13, that's minus 31. Minus 31 plus 8, it's minus 23, right? Let's keep track of this better. So here, let me move this up a little bit so you can see both, like that. Okay, so we have 20 minus 18, that's positive 2, minus 13, that's minus 11. Right? So it was minus, note the algebraic sign, it was minus at A, the function value is minus at B. So there is no zero, there's no zero in between these two, A and B, because the function stayed at the same, on the same side of the, the y-axis, right? If there is a change, see the function stayed on the negative side of the y-axis, right? If it switched signs, algebraic signs, then we could tell that it went from positive to negative or negative to positive. Then that would suggest that there is a zero, a point of transition on the x-axis. So using the intermediate value theorem, determine if possible whether the function f has at least one real zero. So no real zeros between a equals 1 and b equals 2. So this is our final conclusion based on the intermediate value theorem. Let's do the same thing with this one. And I hope that you pause the video for these last two problems and apply the intermediate value theorem to see whether or not we have a real zero in between these two values. So the function at 2 would be 3 times 2 squared. I'm assuming you've done that, and you want to compare your solution with my work here. So 2 squared is 4. 4 times 3 is 12. Minus 2 times 2 is minus 4, and minus 11. So we have minus 15, right? Minus 15 plus 12 is minus 3. So we start with on the negative side of the y-axis, right? Below the x-axis, so to speak. So let's evaluate the function at b equals 3. So that three squared is 9. 9 times 3 is 27. Minus 6 minus 11. Minus 17 plus 27. We end up with positive 10. Right? Positive 10. Very important. So, because so let me write this down. Because there is a change in the algebraic signs, then yes, we have at least Yes, we have at least one real zero. One real zero in this interval, one real zero in 2 comma 3. In 2 comma 3 interval, that's not a point, it's an interval. Oops, sorry, I'm off the screen there. So that's an interval, from 2 to 3. That's an interval along the x-axis. From 2 to 3, we have at least one real zero in this interval. Okay, this is R, and then this is interval, like that. Okay, I hope this matches your answer that you had on your own paper. Let's apply the intermediate value theorem here. So we're going to evaluate this function at these two x values. These are values along the x-axis. So f at -3 is equal to -3 to the fourth minus 3 times -3 squared plus -3 minus 1. Okay, so -3 to the fourth power is positive 81, right? Positive 81, because this is even. Minus 3 squared, that's positive 9, times -3, that's -27. And of course, minus 3 minus 1, that's minus 3 minus 1, that's minus 4. Okay, so clearly the result is positive, right? We can clearly see that. So that's 30, 31, so this would be 50. Positive 50 is, and this is the important thing here, let me write this in red, is that it is a positive value. So let's calculate the same function at -2. Like that. So -2 to the fourth power, that's positive 16. Minus 2 squared, that's positive 4, times -3, that's -12. Minus 2 minus 1. Right? What do we get? We get -14, -15, plus 16, positive 1. Oh boy, we got no shift again, right? It stayed the same. Look at that. It stayed negative for the above function. Here we stayed positive. So once again, no real zeros between these two a values exist. So let's write that down. So no real zero in the interval -3 comma -2. Okay, because the function did not change algebraic signs. So it stayed on the same side of the y-axis. It stayed on, with respect to the y-axis, it stayed on the same side. If it switched algebraic signs from positive to negative, from negative to positive, then we would conclude that yes, it must have crossed the x-axis. Therefore, there must have been at least one real zero. Okay. Notice that this intermediate value theorem can tell us that we have at least one real zero. It doesn't tell us how many real zeros we have in any of these intervals, right? It doesn't tell us that we have, not in that case, but in the middle case, in part B, where we establish that we do have a real zero in between these two, we can only say that we have at least, and let me highlight it there, we have at least one real zero in this interval right there. Okay, at least one. If we have more, we don't know how many more, but we do know that we have at least one real zero there. And real zeros are solutions of the polynomial, right? So that's important. We have a solution of the polynomial at that point. Okay, we have come to the conclusion of another lesson, and thank you all for persisting through these videos. And for now, have a very nice day, and I'll look forward to see you all again next time.